Consider this isochoric process. The gas starts at A at a temperature of 120. What's the temperature at B? Well, let's see. It goes from 2 to 8. You see that? The only way to do that is to increase the temperature. That's what's going on here, is we're increasing the temperature. If we change the pressure by a factor of 4, increase it, we have to change the temperature by a factor of 4. So we can just argue here that this is going to be 480, which is 4 times 120, right? But we can use the ideal gas law to figure this out too. So how many moles are there in the cylinder? Let's see, at A, it's 120, so we're given that, right? And moles is, let's see, PV equals nRT, right? So therefore, N is PV over RT, right? So pressure at A is 2 E5. I'm just reading this. That's our pressure right here. And then our volume is 7 times 10 to the minus third. And then, let's see, we're going to divide by RT. So 8.31 times our temperature is 120. All right, here we go. 2 E5 times 7 E minus 3 divided by 8.31 divided by 120. They're doing a little construction next door, so if you hear something. Okay, so this is 1.40393. I'm going to store that in my letter N for the moles, just for kicks. All right. All right. But we got the right answer. This is good. So what's the temperature at B? Well, if it's 4 times the pressure, it's 4 times the temperature, right? As long as it's absolute temperature. But I know there's somebody that doesn't believe me. So T is going to be PV over NR, right? So T is PV over NR. Okay, so so temperature. So that's going to be, let's see, what's our pressure there? It's 8 at B, right? The temperature at B is 8 E5. The volume is still 7 E minus 3. N is 1.40393. And I'm just going to use, by the way, the value in my calculator. Okay, so let's go 8 E5 times 7 E minus 3 divided by the number I just got, divided by 8.31. And I get 479.999999999 just because of rounding. So that's 480 kelvins. Again, life is short and so is your time on an IB test. So, if you can just make an argument like this, right, it's 4 times. When you do this, right, that'll save you time, right? Okay, so let's see. Let's calculate Q, delta U, and work. Okay, for this process. Well, I know that work is 0 because the change in volume is 0. Work is pressure change in volume. And our change in volume is 0. That's 0. So it's 0. Okay, so we know the work is 0. But we don't know the change in internal energy. But we can figure it out, right? 2 ways to do it. My preferred way would be that the change in internal energy is 3/2 delta P V. This is how I do it. Okay, let's do it. So that's 3/2. And then let's see, what's our change in pressure is 8,000 or 800,000, 85 minus 2E5, and then our volume is 7. Okay, so this is what I would do. This is a shortcut. It's not in the data packet, but there it is, right? Okay. What you want to do, you can also do this, right? And I'll show you this too. 3/2 and R delta T. But let's do this. Let's try this. 3 divided by 2 times left parenthesis 8E5 minus 2E5 right parenthesis times 7E minus 3. And I get that it's exactly 6,300. And the fact that it's positive means that it's a gain in energy, right? So this is our delta U. Let's do this way too. Delta U is 3/2. Our moles are 1.40393. Our R is still 8.31. Our change in temperature is final minus initial, so 480 minus 120. Let's do this. 3 divided by 2 times the moles, which is right there, times 8.31 times left parenthesis 480 minus 120. And I get that this is 6,300, and then comically there's a bunch of zeros and a 1. I'm just going to call it 6,300, right? So that's our delta U. We still have to figure out the work done for this process, so let's figure this out. Oh wait, no, we got to figure out the heat that flows in, okay? Sorry. So we're going to use this. Q is delta U plus work. Now work is 0, right? So our Q is, delta U is 6,300 plus 0. I think Q, therefore, is equal to 6,300 joules. So let me tell you what happened here. We had a closed container that is like a Tupperware that couldn't expand, and we heated it up from 120 to 480, and that caused the internal energy to increase by 6,300, and that internal energy had to come from the heat that flowed into this gas. And so therefore the heat that flowed in equaled the change in internal energy. Woohoo!